In this lecture, we are going to look at the frequency response of this telescopic op-amp. So let us now start naming the nodes. As you can see, the telescopic op-amp has a much larger number of nodes compared to the two-stage op-amp. So let us first point out that any capacitance at the common source node, capacitance will not affect C will not affect the differential mode performance because it happens to be at a common mode node. You should note. So we can ignore the capacitance there because the common source node happens to be a virtual ground. Now let us start naming the other nodes. So let us now name this node 1, node 2, node 3, node 4, node 5 and node 6. So as you can see, including the output node, which is 4, the cascode op-amp has 6 nodes compared to only 2 nodes including the output node for the simple one-stage op-amp. So as you might imagine, every node has parasitic capacitance due to transistors being connected to those nodes. Apart from this, you will also have some load capacitance CL. So everything put together, we will call this total capacitance C4. C4 includes load cap plus unwanted parasitic cap at node 4. So C4 is the sum of the load capacitance CL and whatever parasitic capacitance exists at that node. Apart from this, so you will have other capacitances, C1, C1, C2, C3, C5 and C6. So as you might imagine, the telescopic op-amp will probably have, so it's expected to have 6 poles in its transfer function, because you will have signal current flowing through every one of these capacitances at high frequencies. So if we draw a parallel with the two-stage op-amp, just a quick reminder, in the case of the two-stage op-amp, let us quickly draw out the picture to understand the analogies. So if we look at the analogies between the two-stage op-amp and the one-stage op-amp, so the one-stage op-amp had 2 nodes X and Y, and therefore it had a second order transfer function. So its gain had 2 poles, so 2 poles corresponding to to nodes x and y. So they depended on Cx and Cy. They also depended on the impedance at those nodes. So just a quick reminder. So the dominant pole omega p1 was GDS2 plus GDS4 over Cy, which was the same as 1 over Cy into RDS2 parallel RDS4. In other words, so it is 1 over R out times Cy. So the dominant pole and was the dominant pole because R out was extremely large, and it was also assumed that the load capacitance was large enough so that the combination of these two made this the dominant pole. Apart from this, you also had a second pole which was called the mirror pole, because it came from the current mirror consisting of M3 and M4. So this was given by GM3 over Cx, and this was because 1 over GM3 was the impedance at node x, and the total capacitance as node x was Cx, and as we pointed out, Cx is the could be important because Cx includes and CGS3 and CGS4. Because these two gate source capacitances can be quite large, Cx can be significant enough to affect the phase margin of the op-amp in closed loop. Now apart from this, we also got a 0 whose magnitude was 2 GM3 over Cx. Just a reminder that in reality all of these were left half plane poles and zeros, so I will correspondingly, even though I was writing the magnitude all this while, I will now add the sign to indicate that they are LH, left half plane poles. So this particular 0 arose because the signal took two paths, one through M1, M3, M4 and the other through M2 alone. So this created a 0 because you had two paths, each with frequency dependent phase shifts that were different, which added up at the output to create destructive interference at a particular frequency. Now let us go back to the telescopic op-amp and see if all of these things are possible. So if you look at the telescopic op-amp, you will find that many of these things are definitely possible even in the telescopic op-amp. So the first thing, we have identified that there are 6 poles in the transfer function. Let us find out if there are zeros. As you can see, the path to the output from the signal current from M1 takes the following paths. So the current flows, the signal current that flows through M1 also flows through M3, M5 and M7, and that creates a small signal voltage Vx, and that causes signal current to flow into M4 from M8 and M6. Similarly, the path from M2 flows through the signal current through M2 flows through M2 and M4. As you can clearly see, the signal in the two halves. So in the telescopic op-amp, frequency response, we note that there are 6 poles and there are zeros because I1 and I2 take different paths to the output node. and more importantly these paths have different phase shifts. That are frequency dependent. So this is enough to create a zero, and you will find that because these two paths have multiple transistors and multiple capacitances, the telescopic op-amp will have more than one zero. Now number 3, we'll go back to the main circuit. We noted that there are 6 poles, we noted that there are zeros. The third thing we will note is that the capacitance or rather the capacitance C3 because it includes C3 can be large because it includes the gate source capacitance of M7 and M8. This is the mirror pole. Please note that the mirror pole will be approximately at a frequency that is the impedance at that node, or rather the conductance at that node, which happens to be 1 over GM7. We have calculated that in a different lecture. So the mirror pole will be approximately GM7 over C3, and this would be one of the important non-dominant poles of the system. Now what about the other capacitances? It turns out that the other capacitances C5, C6 and C1 include some gate source capacitances but also some drain bulk capacitances. So therefore we will and their impedance levels at those points are also either very low because they are connected to some sources or they are low enough to cause the non-dominant pole to be somewhat somewhat high compared to the dominant poles. Therefore, the dominant pole of the system is actually 1 over R out times C4, and I'll say this is approximately 1 over R out times CL, where CL is the load capacitance. I will assume this is large enough to dominate the frequency response at that particular node. So this is the frequency response of the amplifier. So if I were to write it as a function of the dominant pole, so the frequency response, so VO by VD of S, would consist of several parts. The first part should be the DC gain of the system. So that is nothing but GM1 times R out. So that is the DC gain of the system. I know that I am going to have at least one pole, which is 1 plus SC4 R out, and I'm going to have a bunch of zeros and a bunch of other poles. So these are the poles and these are the zeros. And since this is the dominant pole of the system, I would expect that the unity gain frequency of the op-amp, of the telescopic op-amp, is dominated by this particular number. If you were to have an idealized telescopic op-amp, the telescopic op-amp should actually be replaced with OTA, and because the output resistance of a telescopic op-amp is larger than that of a one-stage op-amp, this is a better OTA compared to a one-stage op-amp. And its transconductance is the transconductance of the input pair. and if you just show the dominant impedances, that would just be the output resistance in parallel with the output capacitance CL. And now, since we know the dominant pole as well as the output resistance, output capacitance and the transconductance, we should now be able to write the unity gain frequency of the system, assuming that all the undesired poles and zeros are much further away than the unity gain frequency. So you can say that omega u should be equal to, in an ideal case, should be equal to GM1 over CL. As you can see, the R out of the system does not figure into the unity gain frequency of the loop, because the DC gain is also decided by R out, and so is the dominant pole frequency. Now, as you can see, this unity gain frequency is same as that of the regular one stage op amp. In that sense, a telescopic op amp from a frequency response point of view is not that different. You do have a whole number of extra poles and zeros, undesired poles and zeros, but at the end of the day, the transconductance is similar, the unity gain frequency is similar, and most importantly, the telescopic op amp simply looks like a better operational transconductance amplifier because it has a larger R out. Now, let us just draw the magnitude response so that we get an idea of what this would look like if you were to draw the magnitude response of the telescopic op amp. So, at low frequencies, the telescopic op amp has a gain GM-R out that is of the order of GM-RDS the whole square. Now, because R out is extremely large, the dominant pole omega d is extremely small. So, omega d is 1 over R out times CL, and at this point the op amp has a minus 20 dP per decade roll off until it hits omega u, and as you can clearly see, omega u now does not depend on R out, it only depends on GM and CL. Now, beyond this, you could of course have several poles and zeros, so I'll show them somewhat of this manner. So I'll say these are the non-dominant poles and zeros. Now, if you were to overlay this plot on top of the original one stage op amp, I'll now show that in blue. Now, the original one stage op amp had a DC gain of only of the order of GM times RDS. So I'll show that like this, but please remember the R out of a one stage op amp was only of the order of RDS by 2 and not GM RDS squared, and therefore the dominant pole of the one stage op amp will be higher than that of a corresponding telescopic op amp. Now, I'll assume that these two have the same GM and the same load capacitance, and therefore you will find that what you have achieved with the telescopic op amp is simply larger DC gain. So, the telescopic and one stage op amps, both the telescopic and the one stage op amp have the same for a given and a given CL. This is important to note because omega u represents the true speed of the op-amp when placed in feedback. Therefore, the telescopic op-amp has given us larger DC gain, but it will not help in making the op-amp faster.